So let's talk a little bit about control scenarios in PV converters. The common approach for controlling a PV photovoltaic system in a PV converter is to control the voltage. In other words, to extract or to control the amount of power that you extract from a PV is to control the voltage. And the reason is clear, because if you look at these characteristics, there is one point somewhere that the power is maximum. So if you can somehow put a control loop that goes and finds that voltage, you can maximize the power that you extract. Or if you don't want to get the maximum power, want to get less than that. By changing that voltage, you can also change that power. So this is a typical system that we are talking about now, for instance. Now, one thing I would like to mention before, and you might have seen it in this area, is that if you consider a system like this, now for a moment, without any controller, without any converter, without any feedback or something like that, you have one PV panel, and then you connect it to some network, and then you expect that you get some power from this PV panel. Okay, without any converter and without any controller, obviously. So then, if it turns out that this voltage, that the network now biases the PV and generates that voltage, turns out this voltage to be on the right side of this VMP, in other words, in this region, then the whole thing will operate in a stable way. But if it turns out that this voltage is on the left side of this one, in other words here, then it's not going to operate in a stable way. In other words, on the right side of the maximum power point, the system is inherently stable. On the left side of the maximum power point, the system is inherently unstable. Why is it so? It's not difficult to see why it is so. Because, for instance, let's say you are operating at some point here on the right side. Okay? Now, let's say a disturbance happens here in the network, and this more power, let's say a load switches in the network, and more power is needed. So the voltage we see tends to drop, and when VC tends to drop, it goes up, so it generates more power, right? And it stables in another point, let's say here. Now, if again that load is switches off, this goes back to the same point. But if you are here, let's say you are here. Now, let's say one load switches off. So the voltage, one load is connected, sorry, it's better, but doesn't matter. One node is connected, so doesn't matter, connected or disconnected. If it's connected, one load connects, so that means more power needed, so the voltage will drop. When the voltage will drop, the converter will generate, or the PV generates less power. So the network needs more power, and the PV generates less power. And this process will keep continuing until everything shuts down. So that was a very physical explanation of the stability, why this is stable. Engineers discuss the stability this way. For induction machines, for synchronous machines, all of these machines also have a stable region and a stable region. So the same way of discussion can be applied. Okay. So you remember the controllers that we had? I didn't show the diagram again. All these controllers that we had before, for instance, this one, I guess one of these. diagrams, can be used to control the voltage. So there is a capacitor here, and then you apply a voltage here. So you apply a voltage here, and then this follows that voltage. So you can use this controller to control this one, or similar ones. Let me see which one I applied here in this example. Now consider this PV system and a converter here. The PV array comprises two parallel strings, each including 14 series connected modules of this version. I told you in Simulink, you can choose even the brand of your solar panel. Each module has a maximum power of 213 and maximum voltage of 29. The open circuit voltage 36 at 25 degrees. The array will have a maximum power of almost 6 kilowatt at a maximum voltage of 406. Okay, so if this voltage is biased at 406, you will get the maximum power of 5,968 watts from the panel. So you need to design K1, K2, K3 for the current controller to make sure that you can limit the current. So the same design approach. Now if I open the file, open it while we are talking. So this is the characteristics of solar panels. So you will say you will get the maximum power of 6 kilowatt at the voltage of 406. This is current and this is power. Yeah. And I used this controller that we discussed before. Here I use the tight voltage controller because there is no reason to use. You want to use inertia, you can add those as well. I used tight controllers with very small R1. So you see, always you have the choices to make, and that's up to you to make those choices. Whether you want to tightly control the voltage, whether you want to voltage to allow variation and provide support, and so on. Even dynamic support, static support, things like that. So anyway, in this simulation, what happens is that at t equals 0, the converter is not working and the capacitor is discharged, so there is no voltage across the capacitor. The voltage is 0. And at t equals 0.7, which is this point here, circuit breaker closes. The circuit breaker that connects the panels to the capacitor. Is it this one or this one? I think it's this one. This closes. Okay, at this point. So we are feeding 0 power. At t equals 0.9, now converter starts, okay? And between 0.1 to 0.3, the reference voltage of the capacitor is linearly decreased at the rate of negative 1000 volt per second, right? So if you look at the capacitor voltage, once you connect the PV to the capacitor, so initially at time 0, that connection is done. So the voltage, the PV, charges the capacitor. Its voltage goes up all the way to the maximum of 500 or something. That's the open circuit voltage because it's not operating. So the capacitor charges to the open circuit voltage, which is close to 500 volts, I believe. And if you look at this, this shows part of the characteristics. So power goes up and then comes back to zero. So now the capacitor is fully charged, but the converter is not working. At this point, the converter starts working, right? But because the voltage is at the open circuit voltage, no power is extracted from PV. So the converter is working, but no power. Now we gradually decrease that voltage from the open circuit all the way to the maximum and also beyond that. So the reference is this one. So we start decreasing the voltage from the open circuit all the way to the maximum. Maximum is somewhere here, right? 406, and then beyond that even. Go all the way to the left side of the characteristic. Now we have a feedback loop, it's stable, right? The discussion I just gave you said on the left side is unstable. I said without feedback, without control. But if the feedback and control, both sides are stable. So you go to the left side, no problem. The power, see, if you look at the power goes up. Maximum power, you get it here. Then goes down because now you are on the left side of the maximum point. And now increase the voltage again to the maximum voltage, maximum power point voltage, and stay there. And here, in order to show the current limiting property of the converter, because it's very important, we have applied a grid voltage drop from 300 to 100, which is very deep voltage drop. So what happens is that this huge amount of power, which is about 6 kilowatt, right, is coming from the PV, right? And then the grid voltage goes down, so generates huge amount of current. But the converter limits that current. As a result, the capacitor voltage starts going up. And the capacitor voltage is across the PV. So as the voltage goes up, the power goes down. So it's a very nice behavior. Because it's the grid that cannot tolerate power, you know, because they cannot absorb power because its voltage is very low during this time. It cannot absorb a lot of power. So as a result, the capacitor absorbs power and its voltage goes up. So the voltage across the PV goes up and its power goes down. So it's, again, you see this stable behavior. And you see this blue one shows the voltage of the PV. So the voltage goes down, the power goes to zero. This graph here is the voltage of the PV and the reference of that voltage. So because we allowed that to change, you see, we did not use any PI or anything. So we allow that voltage to move around. So in this situation, that's one of the benefits of this approach also. Okay. See if that file opened. Yeah. So this is the scenario here. We have a PV array here. And we have a capacitor. We have a full bridge converter. And one inductance here connected to the grid. And this shows the PV array that I told you. Parallel strings 2, series connected modules per string. Module is user defined. So you can define your own or you can just bring from any brand that you want. See here if you click, see all these different types. And then here, when you plot, when you click on the plot, it gives you that plot. So you can either build your own PV according to what you want, or use the predefined PV panels that are there. Close the other ones. We don't need them. Okay. In these simulations with power electronics, you have to make sure that the time step of the simulation is sufficiently small so it can run the power electronic parts accurately. So that's why sometimes it takes a little longer time, especially during the fast transients. So this is the power, and these are the voltage and reference of the voltage. And this is the current. You may watch the converter modulation index and also the carrier waveform to make sure that it's reasonable and not saturated. No, I haven't talked about MPPT yet. But in practice, yes, I'm going to talk about. In this simulation, no. Yeah, yeah, right. I'm going to talk about that in a moment. All right. And for MPPT, I don't have a simulations. Okay. MPPT, let's talk about that a little bit. Maximum power point tracking. So that the challenge is that maximum power voltage, if you want to extract maximum power, you have to bias the converter or bias the PV panels at that voltage. And that voltage changes with temperature and with irradiance. So you don't want to, we can't constantly measure these two. And even if you measure temperature and irradiance, still the relationship between them and the maximum power voltage cannot be clearly known, or even if you know it for a brand of PV panel, it may change from time in time as you bring the panels in the field. So the idea of using open loop approach to find that voltage or to calculate that voltage is not a good idea. We need to have a feedback approach that goes and looks for that voltage and finds that voltage. That is called maximum power point tracking algorithm that finds that voltage. And then once you find that voltage, you put it in your controller, like this controller that we just discussed for this capital VC. If you put that voltage, that maximum power point tracking algorithm finds, you put it there, then it follows. So how to find that voltage? So this is the approach, basically. You have some panels here, let's say, and this is the converter and the filter and the grid and everything. And then we have a controller that needs a reference for the voltage. We call it capital VC in the previous discussion. Now call it V star PV because it's specifically on PV. Then I need an algorithm that finds this one for me. And that algorithm basically can use the current and the voltage of the PV. And then based on current and voltage finds how much is this voltage back and forth. It cannot find immediately, but kind of back and forth from the history of these two, current and voltage can find out. So how it basically works, perturb and observe is really the common way, is says basically if I'm on the right side of the maximum power point voltage, if I increase the voltage, the power goes down. And if I decrease the voltage, the power goes up. So I look at the trend of these things. If this is happening, I know I'm on the right side. So I will decrease the voltage to approach the maximum point. If I'm on the left side, opposite thing happens. So I will increase the voltage to approach it. That's basically what it does. So it says I perturb the voltage and look at the power, observe the power, and based on the perturbation and observation, I make a decision whether to increase my voltage or decrease my voltage. So basically, so you have a step size, time step size, and a voltage step size. Okay? And then initial value. So you start from some initial value. Typically, it could be the open circuit voltage. So you calculate the power, right? And then you have alpha equal -1 or 1. So -1 for decreasing, 1 for decreasing. So every time you perturb the voltage by either increasing it or decreasing it, and then observe the power, and then see how much power changed. If power increased while you increase the voltage, or if the power decreased where you decrease the voltage, right? That means you are on the left side. You need to keep increasing the voltage. So still keep alpha equal, set alpha equal 1, and then go back to this step again. But if the power decreased while you increase the voltage, or if the power increased while you decrease the voltage, then that means you are on the right side. You have to decrease the voltage. So then basically that's the concept. So the parameters here are basically this time step t and the voltage step size delta v. Time step size means you have to apply these things and wait for some time for the system to converge. So that should be larger than the convergence time of the controller and the system and everything. And the voltage step size means how much you want every time to perturb the voltage. You don't want to take big steps or too small. If you take big steps, you may go over the maximum point. Then you have to come back and then you start oscillating. If it's just too small, it takes long time to get there. But these are easy ways yeah, to find them. You can find them easily, no problem. So mathematically, if you see what we are doing here, and I wanted to mention this also, I think it's good. Mathematically, what we are doing, we are taking derivative of power with respect to voltage, right? And then pushing that to 0. So if you can somehow take or calculate derivative of power with respect to voltage, not with respect to time, with respect to voltage. So one way is to take derivative of power with respect to time and divide it by derivative of voltage with respect to time and divide them together. And then put a controller that regulates this one to 0. If you put 0 here, that regulates this one, this quantity to 0. And then you put an integrator here that gives you V star PV. So this is a mathematical way of looking at the problem. Anyway, but taking derivative is always challenging in practice if you want to take derivative of voltage, because remember these voltages and these currents are noisy, and especially they have switching noises and sometimes other noises, especially in AC systems. So derivative, this is the common approach that I think is good. Just put one simple low-pass filter first to remove high-frequency noises, and then apply this filter, which is again a derivative filtered. So kind of you can say 2 stages of filtering and then apply derivative to minimize the impact of no, noise. All right, so let me go to other one. One simulation here, just to save some time. Okay, so we are done with the major parts of the DC chapter. Now we are moving to the AC. First single phase, and then hopefully tomorrow we can cover the three phase as well. So single phase, basically, this is the statement of the problem. Again, we start with the grid connected or grid following or grid feeding or grid supportive case, and then we move to grid forming. So see, here is the problem. There is an AC grid here. Here is a DC part. So we have some DC assets, whatever they are, PV, battery, or otherwise. And here is connected to the AC grid. So AC grid means single phase. It's a voltage ideally like this. So it has a peak value and a frequency omega. And the current flowing in general will be with the same frequency, magnitude I, and an angle phi. So when you multiply these together, that gives you the power. And that power has two components. One component is unidirectional, if you want, or unipolar. And another component which is bidirectional or bipolar. This is one way of presenting it. Or you can say has a DC value plus an AC value at double frequency. Right? So all the oscillations of the power are at double frequency, and it has a DC value. So the DC value is called the real power, and this peak of the oscillation is called the apparent power, and this magnitude of the bidirectional or yeah, bipolar term is called reactive power, with a negative sign to follow the. So power is a DC plus an AC, and the AC is in double frequency term. Why do I say that? Because if you look at this system, this is the power at this point, right? Let's say we are feeding power to the grid. It has a DC component and a double frequency AC component. And the power, like energy, has to conserve. So you have to have a balance of power. Whatever power goes here, it has to go here, it has to go here. Right? But this power, let's say it's DC, coming from some DC components. That means all the AC power here must be supplied by this capacitor in order to make the balance of power, right? This is kind of a worst case scenario, saying that this power is perfectly DC and this is DC plus AC. So DC comes from this one and AC comes from capacitor. Now, if that AC wants to come from capacitor, that means P2 should be CV, CV, C dot. So it's equal to this one. You can solve this equation and you realize that will give you this equation here. And then you can find VC, which will be, generally speaking, will be a complicated term complicated function. But if you approximate that function, it will give you an DC plus a second harmonic. So the voltage of the capacitor will be a DC plus a second harmonic. There will be other harmonics also, but they are very small, so we can safely ignore them, no problem. So this, let's say how much this double frequency will be. The current will be CVC dot, and then PC2 will be the double frequency power, will be the voltage into the current. So that is the second frequency or double frequency component of the power that capacitor provides. And you look at this, this is the peak of that. This must be equal to the apparent power, or S. And then from here, you can find a relationship between the double frequency component of the capacitor voltage, apparent power, frequency, capacitance, everything. And this equation is very important equation. What it says that if you choose capacitor sufficiently large, then your voltage pulsations will be sufficiently small. Otherwise, those voltage pulsations become very large. Okay? For instance, let's say for a 10 kVA power, 1 millifarad capacitor, 500 volt DC bus voltage, and 60 hertz frequency, if you calculate this one, that gives you 26.5. So you have a voltage 400 volt, and then a double frequency of 26.5 goes around it. I want to show it on a graph. It's like this. So this is the capacitor voltage. This is the grid voltage in this example. Now you have to, one of the requirements, for instance, only look at the converter. Let's say that nobody else cares about that, this pulsation. Only converter may care about that. Is that this voltage should never become lower than this voltage. Yeah, it's a voltage source converter. So now when you change reactive power, that angle phi, this starts moving, shifting, without changing the magnitude. So it could be at points that really goes below this one. So at least for this requirement, we have to make sure that capacitor is sufficiently large. And often in practice, there are other entities which may benefit from that DC voltage. So you don't want to have large ripples across that voltage. Okay. Now, power decoupling. Power decoupling means if I have pulsations here, and if I have a PV panel here, right? So these voltages go across the PV panel. So will be large oscillations across the PV. I cannot do maximum power point tracking very well. And even if I try to do, it will be a lot of oscillation of power. So that's not a good scenario. Can I decouple these oscillations from going across the PV panels? I have these oscillations, but I decouple them from going across the PV panels. Obviously, like we said, the obvious solution is that if you increase the capacitor, those ripples go down and down and down. So by choosing, in this scenario that we just discussed, if you choose 20 millifarad capacitor, the ripples really become 2 volts or 2.6 volts. So probably for that power rating of 10 kilowatt, 2 volts plus minus 2 volt ripple, PV doesn't care about that. But 20 millifarad capacitor of 500 volt is a huge device. And not only is huge, it's very expensive. And also it has a lot of issues, particularly the reliability. Because you need to use the technologies, electrolytic technologies, which are not really very well operating in outdoor conditions for capacitors. So This solution, this obvious solution, is not very attractive. The other solution is if you put another converter here between the panels and this capacitor. And now let this voltage, the DC link voltage, let it have large ripples, but make sure that the other voltage across the PV has no ripples. So these are the approaches for power decoupling. Sufficiently large capacitor, use a double stage. And the third one, which is also used but not very common, is to use completely a separate circuit connected to the DC link to this capacitor, and that auxiliary circuit absorbs the ripples. So you need to have a power electronic circuit again, another capacitor on the other side of the circuit, maybe a smaller capacitor, but you will allow a large amount of ripple on that capacitor. But that capacitor is not connected to anything. You don't mind. So you transfer these ripples from this capacitor to another smaller capacitor, make it large ripples, but remove them from here. So that is also an approach which is used. Okay, so now let's go to control approaches. This is the first one, which is power control method via current feedback loop. So this you are already familiar with in DC. We are going to do that in AC. First of all, if you look at diagram, M multiply into VC, that gives you V, minus VG, pass through this impedance, that gives you the current. This is the model of the converter. Now, in this case, because VC has ripples, you can basically, you have more incentive or more force to use this division. And it's nowadays is very common. Everybody working with single phase inverters, they do this. Even three phase inverters, they do. But single phase is almost there by default, right? So you always divide. If you divide it, that is completely removed. So that is gone. And then now this one also is an AC waveform added here. You can add a feed forward term for soft start and also for helping with the current limiting. That feed forward, if you use a filter that we said in DC, is not going to work here. Because filter will provide a phase shift, and that phase shift will cause a problem here. So what we do, we actually use a phase lock loop here rather than a filter. Phase lock loop is a filter. You can say, look at it, it's like a filter, but it does not provide or does not produce any phase shift. I will discuss that in more details later. So these two initial things we always do, I call them what? Input linearization and feed forward compensation. So this is feed forward compensation, BFF, and this is input linearization. Because this block is nonlinear. So we removed it. So now, as a result, you have a block like this. Yeah. Because remember, this PLL that you put, you only bring in the smooth version of VG. And the grid voltage in AC systems that we are talking always has harmonics of higher terms. So this H of T shows the harmonics that are left. Okay, and this equation summarizes what we did in terms of mathematics. Okay, control structure. Now this is your control system. It has one state variable, right? Our command or reference is sinusoidal, remember. It's not DC anymore. So reference current is sinusoidal. If it's sinusoidal, I need to use a resonant controller, a second order generalized integrator, which has two state variables. So I need two gains, K1, K2, and then another K here 3. So this system is of order 3, and I can find K1, K2, K3 using LQR approach or LQT approach. Calculating and limiting reference current. So how do I calculate this one and how do I limit it? Let's see that aspect. So for calculation, first of all, because it's power, so we need to look at power. If you write down the current in terms of cosine and sine, so cosine is the direction of the grid voltage and sine is quadrature to that grid voltage. So the component that is along the grid voltage, we call it ID, and the component which is quadrature to the grid voltage, we call it IQ. So I always has two components, one along the grid voltage, and one perpendicular to the grid voltage. This is basically related to real power, and this is related to reactive power. And then, based on these definitions that we just gave, you can find real power, which is half Vg I cosine of phi, half Vg ID. So we see real power and real current. You can call it real current if you want, no problem, are related through this equation. And reactive power and reactive current, again, it's a little uncommon to say reactive current or real current, but I think there is no ambiguity. So you can say are related through these two equations. Okay. Now, if you define these cosine and sine functions as SD for direct and SQ for quadrature, cosine of omega t and sine of omega t. So the direct term is parallel with the grid voltage and the quadrature is perpendicular to that. Then, now we've proved this equation. I reference is ID SD minus IQ SQ. ID is 2p set over Vg. IQ is negative 2q set over Vg. So this very simple calculation tells you how to calculate the reference current, but leaves a few questions open. Where do I get sine of omega t? Where do I get cosine of omega t? Where do I get Vg? And also the limiting. So these questions basically in practice nowadays are answered by PLL. So PLL provides all these three signals, SD, SQ, and VG. And then once you have SD, SQ, VG, and power set point, reactive power set point, you can calculate them, and then you have the reference current. So for that reason, here, okay, this shows the limiting side. So for limiting, it's very critical. We cannot do the limiting when it's sinusoidal waveform. We should do before it becomes sinusoidal. So you calculate P set divided by half Vg, which is ID, and IQ, right? These two components, you first calculate them, ID and IQ. And now you look at ID squared plus IQ squared. That shows the magnitude of the current. You limit that here, saturation, right? And divide the limited value to the actual value, and now you multiply back to this one and then bring it here. Now, this new variable here is equal to this one as long as you are within the normal range. When the current goes above the range of operating and becomes beyond the limit, this limiting fact causes this one to stay there, doesn't go above that. So, and the same thing for IQ. So ID and IQ here are the limited versions of this one and this one. And once you find them here, you multiply into SD and SQ, and then subtract them. That gives you I reference. So this is the limiting approach for the current. And these are the equations if you want. Some people are more comfortable with equations, some people with the diagrams. The diagrams tells everything, but if you want to see them in the equations, these are also there. Okay, now it looks like the only thing is missing is how this PLL works. So let's talk a little bit about how PLL works. I think we have 10-15 minutes. I think we should be able to do that, or a good part of that. So, and for PLL, I explain here PLL that we ourselves developed, and we called it Enhanced Phase Lock Loop, EPLL. And that is here. This part here is the PLL that people used for many years, and we added these parts to it and became enhanced PLL. So it receives the grid voltage and it does some calculations. The calculations are basically three integrators, one for magnitude, one for frequency, and one for angle. So basically three dynamics that search for the magnitude, angle, and frequency of this waveform and try to find them. One of them eventually finds the magnitude, one of them finds the phase, and one of them finds the frequency. And this is the rated value of frequency here. If you apply it, it will have a faster startup. So you can look at this diagram. It generates a tracking error, pass through these equations, and you can write down the equations. I don't know if I wrote, but it's not necessary. So that's basically what EPLL is, the basic block diagram. Now, for analysis, just to make it simple without going into too much, you can imagine there is too much mathematics and these things here, and we cannot go into details. So if I want to give you a simple analysis to get to the core a little bit, let's say mu3, and this mu1, mu2, mu3 are three controlling parameters of PLL, EPLL. Let's say mu1 is equal to mu3. So the gain of the magnitude loop and the gain of the phase loop, they are equal. And for a moment, let's say the gain of the frequency loop is 0. So the frequency is exactly at 60 or 50. Then if you write down the equations, become this one and this one for magnitude and phase just by looking at the diagrams, right? And then if you manipulate these equations a little bit by defining the new state variables of x2, x1, and x2 here, you will end up with a linear equation like this. x1 dot equals negative omega x2 plus mu1 e, and x2 dot equals omega x1. What did we prove? If you look at this diagram, it's heavily nonlinear. It has few multiplications, right? One here, one here, one here, and the sine function and cosine function, so very nonlinear. We proved that under these simple conditions, if mu3 is equal to mu1 and mu2 is 0, frequency is 60 or 50, which is reasonable. It's a good approximate. That becomes completely linear. And by the way, this division is very important to bring to this condition. And this is what we added. It was not there. So by adding this division, we linearized the PLL. Okay. And then if it's linear, you can derive its transfer functions, and you will see it has two transfer functions. From this input to this output, that's this transfer function. So it generates the waveform which is parallel to the input. And this is the waveform which is quadrature to the input. So this is in parallel, and this is quadrature. So the one that is parallel is basically a band pass filter. So a band pass filter removes all the low frequency and high frequency noise, or mitigates them, and keeps that frequency that we want without introducing any phase delay. That's what I said before. A band pass filter, second order band pass filter, does that. And this is a low pass filter, so for the quadrature. But again, that means at that frequency is 90 degrees phase shift. So for the quadrature, we need 90 degrees phase shift. Okay, now another thing that we can get from this analysis is that the transfer function has this denominator. If it has this denominator, we know where the poles are, so we can choose the value of mu1 and mu3, which are equal, to get the poles that we want. So if you want to have this equal to this standard second order equation, you will find mu1 equals 2 zeta omega 0. So this gives you a guideline how to design mu1, 2 zeta omega 0. Zeta is a damping factor. If you want to have a damping ratio of 0.7, you put it there, and then you will get it. If for a value of 0.5, mu1 becomes equal to omega 0. And the poles are here. For 60 hertz frequency, these are negative 188 plus minus J327, the poles of the transfer function, which indicate a desirable time constant of around 5 milliseconds. So that will be the rough estimate of the time constant of the PLL. It takes about 5 milliseconds to have the time constant, maybe 20 milliseconds to 25 milliseconds to achieve its response. Okay, so this discussion basically ignored the frequency loop. And it's very good discussion because in power system, the frequency does not change significantly in power system that we have. But if you want to get more insight, we need to include that frequency loop in our analysis. And also we need to design the gain mu2 anyway, right? So we need to do further analysis without ignoring this block here. So for that part, this is, like I told you, this is a standard PLL. People have been able to linearize this PLL using Jacobian linearization around the equilibrium point. So we did the same thing here. So this is Jacobian linearization of the frequency phase angle loop. And then you will find a transfer function. And then from this transfer function, you put it equal to the standard second order polynomial. And then you can find mu2. So mu1 and mu3, you put it equal. And then you design it here from this equation. And for mu2, you design it here. You only need to choose two damping ratios. One damping ratio here for the magnitude and phase angle, and one damping ratio here for phase angle and frequency. Okay. So summarized everything in this algorithm. Let's say the only thing we need to know is the frequency of the grid voltage. And then we are going to design mu1, mu2, mu3. Choose the damping ratio zeta and calculate mu1, 2 zeta omega 0. The recommended range for zeta is 0.25 to 0.75 based on our experience, and it's a reasonable range. The smaller ones give you more stronger filtering, but actually make it a little bit slower. And then mu3 and mu1 equal. For mu2, use this equation, but you need to choose C, this another damping ratio. This is the damping ratio of the frequency. Now, frequency in power system is not a fast changing variable. So you don't need to choose a small damping ratio. Even a large damping ratio is good. So the recommended range is between 1 and 1.5 for estimating the frequency. Okay. Now, this EPLL here that we just talked about is the core diagram, core structure of the EPLL. At least we need two modification or two important modification that if you want to use it in practice, if you want to really build it in your practical setting. In simulations, no, not necessary, but really in practice, and you will see why. So two modifications on to the PLL. Okay. And they are shown here. One is here, another one is here. So this one, what it does basically, it adds another loop to the PLL. And this loop is a simple integrator. Just one integrator multiplied into another gain, mu 0. So we have mu 0, mu 1, mu 2, mu 3 now. What it does, it says if the input signal has any DC value in it, I will also estimate that DC value. Now, in practice, we know that the grid voltage doesn't have DC, right? So why do we need to put it here? The reason is because whenever you want to implement something using digital control and everything, so you measure things, yeah, with sensors, you measure things, you bring them within the range, plus minus 2 volts or something, and then in order to bring it into the microprocessor, you need to shift it up, right? So you need to shift it up, and then inside your microprocessor, you shift it down. So the shifting it up you do using hardware, but shifting it down you do using software, inside your software, right? Okay. So how do you make sure that these two are exactly equal? This is a big problem. This is really for those that have done in the worked in the lab or in practice, you know, this is a big problem. And for the first time, when we implemented this many years ago, the fact that this loop was not there would not let us get results. And we was wondering what the reason was. The reason was there was this DC added as a result of this procedure to the waveform, and then when a DC is added, PLLs generally are sensitive to DCs. So if you have some DC, even 10%, 8%, 5%, the results will start really causing a lot of errors. So you need to remove it. Okay, so this removes the DC. This one here, what it does, it basically, if you look at this, how it works, the mu2, gain mu2, divides it by 1 plus lambda into absolute value of this point, x. Sorry, x. X is here. So what is x? X is the error divided by a. So what happens again, this is again a practical thing. And when phase jump happens in grid voltage, in AC waveforms, and when that happens, when transient faults happens, or when local loads switch in, so if you really observe the grid voltage, you will see a phase jump happens. The voltage jumps 5 degrees and then continues, local voltage. As a result, if you don't have this one, you will see your frequency also experiences a oscillation, frequency of the power of the PLL. The grid frequency did not change, only phase angle changed, but the PLL shows an oscillation of the frequency. You know, because phase and frequency are related. So in actual power grid, in actual voltage, frequencies did not change, only phase changed. But in the PLL, frequency also changes. So what it does basically, it says during that time that the error suddenly changes, I will decrease the gain of the frequency loop. So I will not allow the frequency to change. So by choosing this lambda, a number like 10, 20, that this is our experience, you can significantly decrease this problem. And this saturation block here, after you estimate the frequency, you will put plus minus 5 hertz, plus minus 4 hertz, depending on how much you want to uh, tolerate. Okay. Here is a discussion how to design this mu 0. I'm going to skip that. You can read yourself. And a couple of very nice graphs here. For instance, this shows a summary of how you design mu 0 after this analysis. It says once you choose mu 1, because we already talked how to design mu 1, once you choose mu 1 divided by omega 0, that's this axis here, and this axis here is mu 0 divided by omega 0. So let's say mu 1 divided by omega 0 is 0.8. Then you go up here, and then you find your mu 0. But this comes from this analysis here. Very simple analysis, but I don't want to spend much time on this. Anyway, simplified now or summarized in this algorithm. Again, what is given is grid voltage frequency. And then we would like to design these 5 parameters now. So first mu1, the same approach, zeta between 25 to 75, and then mu3 equal to mu1. We found no reason to not choose mu3 equal to mu1. And then define mu1 bar, mu1 over omega 0, and then from that graph, find mu0. So that's the way to find mu0. Mu2, we already talked about how to find mu2. And lambda, our experience is any number between 10 to 30. So let's say put 20, that gives you a very good reduction of those fluctuations that I just talked about that happens. All right, I think we can take a break and start sharp at 12.